Welcome to the first module of this DTrace training. This module is titled Getting Started, and there's a good reason for that. In this module, I'd like to show you different aspects of DTrace. For example, what is DTrace? A brief history so that I can explain where we are today, how to get your copy, how to run a DTrace program, some terminology and concepts, and a first example. The example has been chosen to not be very simple. It's not a simple print statement, but it's also not overly complicated. But it has several of the key ingredients that you'll find in a DTrace program. I'd like to show you what does it take to write a DTrace program and how does it work. What is DTrace? It all started when engineers were running into the following situation. There's a complicated system and something unexpected is happening. For example, all of a sudden the response time becomes very long. System gets really slow. Well, how do you determine what it is doing and why without any drastic action? So you can't take the system down, it's running in production, and you really would like to get more information without sort of anybody else being bothered by that. And that led to the development of DTrace. My simple one-line description about what DTrace is it is your microscope into the operating system. You will be surprised to see how much DTrace can show you about what's going on when you're, for example, running your application. What is DTrace? DTrace is a tracing tool. It traces activities in both userland and the kernel. And one of the nice features of DTrace is you can combine this. You can look at the whole top to bottom tracing. So you start your application and then all the way down into the operating system, DTrace can follow it and you can see what's going on. That makes DTrace ideally suited to troubleshoot problems at the OS level. You also have full control over what needs to be traced and when, because as you will see shortly, you're going to program DTrace. You're going to tell it what to do when something happens. And typically the way you use it is you cast a fairly wide net and then you zoom in on an activity of interest so you can go deeper and deeper. DTrace has been designed to be safe for use on a production system. For example, it doesn't have loops. And what I like very much is it's easy to use. How does DTrace compare to other tracing tools? There are many tracing tools out there. Truss, strace, ftrace, netstat and perf are just a couple of examples, but there are many more. Well, the big message here is DTrace doesn't replace any of those tools, it adds to the list. It's just another tracing tool in your toolkit, and as I hope you will agree with me, it's very powerful. It can do a lot of interesting things and help you troubleshoot problems. DTrace is a programmable tracer. You write scripts or programs in a language called the D language. The D language is specific to DTrace, but it's like C with a bit of flavor of awk and a bit of shell programming. It's not that exotic. If you have experience in any of those kind of programming environments, you will find that the D language looks very familiar. With this, you get flexibility, plus access to detailed information. For example, you can print the arguments in a function call. That could also be a kernel function or a libc function. In that way, you can really find out what's going on. For example, let's say you're interested in memory allocation. Well, you can trace the malloc call and you can see what argument is passed in, so you can see the sizes of the memory blocks being allocated. And as I just mentioned, one of the other nice things is that DTrace provides a holistic view. You can look at the application, you can look at the kernel, or both. And that's really where DTrace shines. Another very nice thing is the flexible reporting. You control the output. You can make it look the way you like it. You can show whatever you like. You're totally in charge of that. A little bit of history. It all started in 2004 when Sun Microsystems came out with the Solaris 10 operating system and it had DTrace included. In 2010, the port to Oracle Linux started and it was completed in October of 2011. Then in 2013, 2015 and 2019 updates were released. The one thing is using DTrace required some invasive kernel patches to be installed, and that was not always desirable. Actually, Apple and Microsoft, they both have DTrace. There's a DTrace in macOS and there is one in Windows, so that's kind of interesting. But at some point something very interesting happened. The decision was made to re-architect DTrace on top of eBPF. eBPF stands for Extended Berkeley Packet Filter. DTrace also leveraged some other Linux tracing features, but by and large it's built on top of eBPF. That work started in 2018 and the first release came out in 2020. Since then, regular updates have been released and will continue to be released. If you're using DTrace, please stay in touch about updates. What I call today's DTrace is built on top of eBPF. It generates an eBPF program that's going to execute code in the kernel. DTrace will compile your D script or program and will compile that directly into an eBPF program, and that's going to be executed. It is a user space only design. DTrace installs like any other package, which is really nice, and the need for those kernel patches has been eliminated. How do you get your copy on Oracle Linux? Well, DTrace is available for Oracle Linux 8 and Oracle Linux 9. It's available for x86-64 and ARC64. In other words, it's available for Intel, AMD and ARM. And depending on your situation, the hardware that you use and the version of Oracle Linux, these are the repos where you can find DTrace. Installation of DTrace is as simple as the following. You tell the config manager which repo you want to enable and you do an install DTrace. In this example, I want to install DTrace on an x86-64 system running Oracle Linux 9. Sudo dnf config manager with the enable command will enable the correct repo. I do a sudo dnf install DTrace and voila, I have DTrace on my system. As a side comment, if you want to know which Oracle Linux repos are available, you can always go to yum.oracle.com to check it out. You can also build and install DTrace from the source. There's a GitHub repo. That's where you can find DTrace. The URL is given here. You can look at the source code. You can download and build and install your own DTrace if you like. I'm not going to talk about that anymore in this training, but I just wanted to point that out. How do you run DTrace? First, a big heads up. Verify that the correct DTrace executable is used because SystemTab provides a tool that lives in /user/bin and it's called DTrace, but that's not the DTrace that we're talking about here. So make sure that you pick up the right version. You can use the which command as is shown here to make sure that it's the DTrace from user/bin that you're going to use, or you can use the capital V option to check the version number and that you have the correct DTrace. Make sure to do that because in the past some people have fallen into that trap. They thought they were using DTrace, but they were not really using the DTrace that we talk about today. How to run DTrace? Well, given that DTrace generates an eBPF program, it also probes some programs it doesn't own. Root privileges are needed. You always run DTrace under sudo. Don't forget that, sudo DTrace and then whatever you want to do. That's the way it works. That's very common for the system-wide tracers, and DTrace is no exception. There are two ways to use DTrace. There's the command line way that I'm showing here, where you put your DTrace commands at the command line, sudo dtrace -n, and then whatever you want to do with DTrace is followed next. For example, here I'm using the so-called begin probe that I will explain later, and all it does is a simple print statement, and that will work. That's a valid DTrace program. The thing is, once the situation gets a bit more complex, this may not be the best approach. And my favorite approach is to put the DTrace language constructs in a file that in this case are called script.d. That's, by the way, a convention. The convention is to have those scripts or programs end with .d as an extension to make clear it's a DTrace program. It's not required, but it's sort of convenient. So now I have defined that begin probe with the clause printf in my script, and all I need to do is execute that script from the command line. Sudo dtrace -s, because I'm going to read from a file, script.d will execute this simple probe. Again, my personal recommendation is to use scripts, but of course the choice is yours. Terminology and concepts. With DTrace come some words and concepts that I would like to explain now. Probes and providers play a crucial role in DTrace. You'll hear me saying that a lot. A probe is nothing more or less than an event that is available to trace. Probes are predefined in the system. I'll show you in a very short while how you can list all the events that are available to be probed, and you select from those whatever you like to do. For example, you may want to trace the entry to a specific kernel function. When that happens, when that kernel function is executed, you define the actions that need to be taken. If you'd like to list all the available probes on the system that you're using, use the -L option. Sudo DTrace-L will list all of them. Probes are organized in sets called providers, and the name of a provider is used in the definition of a probe. And on the next slide, I'll show you examples of that. What you're going to do, you're not only going to select a probe, but you're also going to tell DTrace what you want to do when that probe is activated, when it executes, or the terminology in DTrace, it fires. The probe fires, and then you're going to tell DTrace what needs to be done. You do that in a language called the D language. I just mentioned that a little while ago. That's a sort of C-like language with awk and shell script kind of flavors added to it. For those of you familiar with either one of those languages or all of them, you will find the D language to be quite familiar. And that's your way of telling DTrace what to do. The actions that you define, they're called a clause. They're grouped together, so it's like a code block, and that's called a clause. And here I show you the output of the DTrace-L command. Always use sudo DTrace-L, and then I can count, for example, how many probes there are. Well, this includes a bit of header information, but by and large we see that there are over 110,000 probes on this system. That's a high number, but that's also quite typical. You'll see that you have access to a lot of probes. If I just do sudo DTrace-L now, there would be more than 110,000 lines on the screen. So what I've done, I'm showing the first 5 and the last 3. And what we see 5 columns. The first column has the probe ID. Every probe has an ID. Then there's this provider. Remember, the probe is part of a provider, and we see that DTrace is a provider as well. It has some special probes that I'm going to talk about soon, and that's one of the things you could trace, for example. But there are many, many more, including the CPC, that's for hardware event counters, syscall at the bottom, and those are all the providers are listed there that you can choose from. Then in the third column, we see module. Well, a module is the name of a kernel module, a library or user program in which the probe is located. How do you use that? Well, in that way you can restrict. You can say, well, I'm only interested in this kind of context, only if it's in this module. You don't have to specify that. I'll show that on the next slide. But in this way, you can either cast the net a little wider or tighter. That's the purpose of the module. It's very useful. Then the fourth column is titled function. That's the name of the program function in which the probe is located. And what we see here at the bottom of this output, we see 2 functions, bind and socket pair, and that's followed by a name, and the name is the event that you can actually probe. For example, this shows me that I can probe the entry into the bind function. Well, actually I can also probe the return, but that's not shown in this output. That's shown for the socket pair. You can see for the socket pair function, you can probe the return and entry into that function. That's the kind of the toolkit that you have available. Those are the probes that you can choose from, and you make your choice about which one you want to use. How do I use that information to define a probe? Well, a probe definition consists of 4 fields: the provider, the module, the function, and the name. For example, as was shown on the previous slide, one probe could be the syscall provider with the VM Linux module, the bind function, and the name would be entry. I want to probe as soon as the function bind is executed. That's when some action should be taken. And again, the action is under my control. You can leave out fields. These act as a wildcard, so you say, well, I don't care. And that gives you a lot of flexibility, actually. It's very useful. You can also use wildcards in the names, and that's shown in the example here at the bottom. I want to use the syscall provider, but I don't care which module. I don't care where it comes from. But what I do want to see is every function where the name starts with write. That's what write star means. Every function starting with write should be probed. And what do I want to probe? I want to probe the entry into those functions. That will give me access to potentially a lot of probes because of the star and the wildcard. Very, very powerful, very flexible. And that brings me to the definition of a probe and a clause. This is what it looks like in your DTrace script or program. We have the probe, that's the provider, module, function, and name. And we have the actions. For that, you use the D language to define what you want to happen whenever that probe executes or fires. That's called the clause. But there's a thing with this that you need to know. The probe will fire as soon as those conditions are met. And maybe you want to restrict only seeing that probe being active in a way under certain conditions. And that's where the predicate comes in as a very, very useful feature in DTrace. The predicate is enclosed in forward slashes and it behaves like an if. It's a logical expression and it evaluates to true or false. If the expression evaluates to true, those actions will be executed. If it evaluates to false, it doesn't. And that's a surprisingly powerful mechanism to control when actually probes are producing output. And soon you'll see an example of that. So that's called a predicate. To summarize, a DTrace script or program consists of a collection of probes, one or more. Each probe definition is associated with one or more actions. You define those actions. That's why you need a D language to express what you want to be done. And then there's the predicate, that's optional. If you leave it out, the actions will always be executed, but with the predicate you can control when those clauses are going to be executed. That gives you some sort of if statement like condition. I've mentioned this a couple of times already, the D programming language. That's what you can use to define the actions that need to be taken. It is similar to C, it has some awk and shell scripting flavor to it. So again, if you're familiar with one of those languages, you'll find the D language to be quite easy to learn. The D language includes variables, aggregations, operators, intrinsic functions, but no loops, for example. So you cannot have the situation that the program hangs in an infinite loop that never ends. You can also set options and tunables through pragmas, dpragmas. You can put them any way you like, and here's an example. It's actually my favorite example. It's pragma D option quiet. That will silence DTrace itself. Otherwise, DTrace will produce some output, and in general, I don't like to see that. I want to control the output. I sort of silence DTrace so it won't show me those messages. The predicates, I just talked about it, but let me repeat it. They're very important in DTrace. They're used for control flow. A predicate is enclosed in those forward slashes, as you saw, and it's a logical expression. It evaluates to true, or better said 0, or false, or better said non-zero. If it's true, the associated actions are executed, and otherwise they're not executed. And here's an example. It's actually quite a common example. The predicate is pit equals $target. What does that mean? Well, when a probe fires, it has a process ID. That's the process ID that's causing the probe to fire. $target is the process ID of the target that I'm looking at. You can do that with DTrace. You can say, well, I only want to look at a certain process or command. That process ID is stored in $target. What I'm here demanding is that I want you only to do something if the process ID of the probe matches the one from the target. In other words, I don't want to see anything else than what corresponds to my target. And that's a very common and very useful use of a predicate, but you can do more things with predicates. How does it work under the hood? After you start DTrace, a program is actually, an eBPF program is generated, and that is compiled. Your D script is taken, that's translated into an eBPF program, And under the hood, that's compiled. You don't see it, it's transparent to the user. And if there are no errors, execution will start. That all just happens. And unless you have quiet mode enabled, you'll see a message like this where DTrace echoes how many probes have been matched. That's very useful to look at. That's the kind of output that DTrace produces by default. And if there's an error in your script or program, this is where it will show. At runtime, when the conditions of the probe are met, it's executed, or the DTrace language it's set to fire. The probe is set to fire. That's when things start to happen. And each time the probe fires, the corresponding code is executed. Unless there's a predicate and it evaluates to false. If there's no predicate, the code will always be executed. If there is a predicate, it will only be executed if it's true. If it's false, nothing will happen. There are special probes available, including begin and end. The begin probe fires when tracing starts, and the end probe fires when tracing ends. And you can use that for example, the begin probe to initialize certain variables, and the end probe is typically used to print results. Let's look at a first example. This is a fully working example, and I want to show it to you all the way from start to end, from sort of the design and then how it executes. And the idea is that it hopefully helps you to understand how you use DTrace, the kind of things you can do. You can do a lot more than what I'm showing here, but this will be your first example in doing things the DTrace way. Let's say it's Monday morning 9 AM and the following mail arrives in your inbox. Hey Ruud, I've got a question for you. Which kmem_cache functions are called when I execute bad CMD? Oh, and I also need to know how often they are called. And did I tell you I need this for the all-important meeting in an hour? Thanks. Okay, so what's being requested here? Well, clearly there's a command called badCMD, bad command, that's of interest. And apparently it's calling functions that start with the name kmem_cache. The question is, which ones are called? Apparently there are more than one. And how often are they executed? The way I go about this is I first design the core part with one or more probes that deliver the functionality that I need, and then with some things around it. And that's what I'm going to show you. In this case, we're interested in functions starting with kmem_cache, and the DTrace-L output showed me they're part of the FBT function boundary tracing provider. That's what I know. That defines my probe. I don't care about the module because that was not requested. That's why you have the double colon after FBT. I use the star, so I capture every function starting with that name, kmem_cache, and I want the probe to fire when I get into one of those functions. That's what the first line does. Then we have our actions underneath. But there's a problem. This could produce a lot of output because everything that meets this requirement will cause the probe to fire. That was not the idea. The idea was it should be in relation to this bad CMD. That was the one that we're going to try to analyze. This is where the predicate comes in, and it's the same predicate as I showed a couple of slides ago. The PID equals $target. With that, I'm going to restrict all the output to only those things that happened when I execute my bad CMD and nothing else. Everything else is ignored. And that's the power of these kind of predicates. In that way, I can fully control the output and certainly dramatically reduce the volume. And I don't care about those other things, so why would I? That's the predicate here. And then we have the actions. There's only one action. And let me explain that. Well, the question was, can you count how often those functions are called? And it turns out there's a function, it's a so-called aggregation function. You can find them in the reference manual. And that does the counting. That increments a counter each time it's called. That's doing the counting for me. Now, since this is a special function called an aggregation function, I need to store the result in an aggregation. And that's what the @ symbol here is used for. It tells DTrace that I'm going to store the results of an aggregation function in a structure. It's like an associative array that I call D_calls. That's completely my invention. That's your choice of a name. And I named it D_calls. And I'm going to use a key. It's like an associative array. And I'm going to use two fields in that key, I'm going to use the variable exact name and the probe func variable. What is that? Exact name is the name of our target. We know that's always going to be bad CMD. In this case, this is not needed. I put it in for demonstration purposes, but the whole thing would work fine without that exact name, but I just wanted to put it in. And as a little side thing, if you would use this for some other thing than bad CMD, the name of the other thing would show here. So it gives you some flexibility. Probe func is the function that actually caused the probe to fire. So that's one of those kmem underscore cache functions. In that way, I capture the behavior. I store everything in that structure called the calls, including the count and the probe func, and in this case also the exact name. This is quite a common thing you'll see in DTrace programs, by the way. We got our main probe defined. Now what do we do next? Well, I could just run that probe. I could put that probe in a script and run DTrace, because aggregations are always printed. You don't have to print them. They'll automatically be printed upon completion, so I wouldn't have to do anything. But for demonstration purposes, and also to demonstrate what I mentioned in the beginning, the flexible reporting, I'm going to show you how you can use DTrace to actually get a nice table with the information. And I'm going to decide what information to show. That's the kind of flexibility that I've mentioned several times. We start with the begin probe. The begin probe is executed once when the tracing starts, and it has a simple printf statement. Exactly the same syntax as in C. I have my format string, and I'm going to print 3 strings, target, function, and count, and those are going to be the header of the table that I plan to print. That's what this will do, and nothing more, nothing less. The end probe is a little bit more complicated. And again, aggregations are automatically printed. I would not have to do this, but I want to show you how I can customize the output. The end probe is executed when the tracing ends. So that's the last thing that you do. By then, all the information should be available. I'm going to print my aggregation at the underscore calls. And I'm going to use a format string and a special function. Since I'm printing an aggregation, I need to use the printA function. And I use a format string. The first two, remember the key consists of 2 fields, the exact name and the probe func. So I'm going to print them in a fixed format in my table. And then I want to print the result of the aggregation. The result is the count. That was one of the things that was requested. And that's an integer number. If this was C, you would write a %d or a %6d, like in my case. But this is the result of an aggregation, so I need to have the @d symbol. So I need to use the @ symbol. And again, this is a little bit more complex than really beginners material, but I want to show you how you can use DTrace to get this all done. We're almost there. A little bit of customization. I don't like typing in DTrace all the time, so I put that in the first line in my script, the interpreter line. I add some C-style comment. You can put it any way you like, and it's very convenient, of course, to add comments to your script. And I'm using my pragma-d option quiet to suppress the header line and the CPU and ID columns, because I want to have full control over the output. Now, before I show the full script and the output, a little intermezzo. How does a D script actually execute? D and DTrace provide actor-based programming. It's concurrent programming. If you're interested in what that means, there's a good Wikipedia page, and the URL is given here. A D script is a collection of clauses, and recall a clause is a code block with an optional predicate. And a clause is associated with 1 or more probes. I haven't mentioned that before, but you can have a single clause associated with multiple probes. And actually that's quite common in DTrace, because it's quite common that for different probes you want to have the same action. That's very convenient. You don't have to repeat code. You group them all together, and that's very nice. And that's how probes and clauses are related. The D script is actually processed from top to bottom, and the probes fire in an asynchronous way. When the conditions are met, a probe will fire. But There's also a sequential part, a serial part. The actions associated with the probe are executed in program order, and the clauses with the probe are executed in order. So there's definitely an order there. The thing is, the probes, they fire whenever the conditions are met. They're not necessarily or typically will not execute in the order that you write them down in your script. I also should mention that in order to make this efficient, quite some implementation optimization has been done to make this work very well. This is the full script. I call it count-kmem.d. Putting it all together, I'll do that fairly quickly. We've seen all the components already. The first line is the interpreter. Then we have some comment, the pragma, the begin probe, the what I call the core probe with the kmem_cache probes, and then the end probe. And this is a good moment to again explain how this executes, because I put the end probe at the end, but I could put it anywhere in the script. What I do know, it is actually executed when the tracing stops. Likewise for the begin probe is executed when the tracing starts. The other probes, I don't know when they will go off. Don't be misled by the order in the script, because at runtime the order could be different. But this is what my full script looks like, and we're going to execute that. This script delivers the following result. I'm using sudo, always use sudo, to execute my D script. As shown here, I use the -c option because I want to trace what happens when I execute bad CMD, and because that was the request. And what the output shows is the following. The target column always has bad CMD. I know that, I mentioned that, that's kind of a little bit of redundancy here. I have 5 function calls apparently, and the counts are shown in the third column. Yes, I have achieved my goal. I now know which functions are called and how often. And guess what? It's only 9:30. There's still time for a coffee. We accomplished our goal. I hope that this has been useful to give you a good idea what DTrace is about and how it might help you in troubleshooting. In case you are interested in DTrace, there's an excellent reference guide. I can highly recommend to read it. It's very well written, has lots of examples, and explains many things in quite some detail. The URL is given here. You can either read it online or download the PDF. The choice is yours. But again, definitely recommended reading. Thank you for watching.